Okay, so solving index equations. Now, when we have an index equation such as 5x is equal 5 to the power of x is equal to 18, we can solve this in exact form by just rewriting it in logarithmic form. So that is x is equal to log base 5 of 18. So this is a legitimate answer that gives you a legitimate number, and we can leave it like that. However, we could use, in fact, we could give an approximation solution by doing the change of base to convert it to base 10, okay? So the idea is, if you're being given this equation, okay, you're going to start off by writing it in log form, so as this, but then we're going to rewrite log 5 of 18 as log base 10 of 18 over log base 10, or our new base, of 5, okay? And so this is going to give us an approximation value. So again, we're going to put this straight into our calculator of 18 over log of 5, and that should be over, hit equals, and we get 1.79. Okay, so this is the way, it should be 1.8, but this is the way that we can actually solve these problems out, by getting an approximate value. Okay, so let's have a look at some examples, and we're going to jump straight into some very similar looking type of questions. So solve these equations, correct 4 significant figures, then check your approximations. So 4 to the power of x is equal to 11 is our part A. So we're going to start off by rewriting this in logarithmic form. So this is log of base 4 of 11 is equal to x. Okay, so just going to swap them around. So that is log of 11 over log of 4. Now, even though the calculator doesn't have the 10 there, it's a very good habit to write it down so that we know that the bases are the same. So x is equal to, we're going to put that straight into our calculator. Okay, log of base 11, not that, 11, log base 10 of 11 over log base 10 of 4. Okay, and we get 1.7, we get 1.7297, so 1.730 to 4 sig fig. Now, to verify our answer, what we're going to do is we're just going to put it back in. So verify by subbing. So we get 4 to the power of 1.730, and that should be very close to 11. So 4 to the power of 1.730, and we get 11.0. 43, which is pretty close to 11. Okay, so we're pretty happy with that. So let's go to the next one. 5x is equal to 0.03. Okay, so same thing again. I'm going to rewrite this in logarithmic form. So it's going to give us x is equal to the log base 5 again of 0.03. Okay, so to rewrite this in change of base form, it's going to be log of 0.03 over log. We should be having those 10s there as well. Log 10 of log base 10 of 5. And then we're going to get our answer by substituting in. So log of 0.03 over log of 5. Okay, so it gives us an answer of approximately negative 2.179. That's to 4 significant figures. Okay, so we can verify the answer again by substituting the value in, but I'm going to try to verify it by putting our change of base in. So by subbing x is equal to, and this is something that you wouldn't be expected to do every single time, but I'm going to verify it by substituting this change of base back in, okay? So our original equation was 5 to the power of x is equal to 0.03. So I'm going to verify this by putting 5 of log 10 of 0.03 over log 10 of 5. Okay, and that should give us exactly 0.03 this time because it's not approximating. So 5 to the power of log of 0.03, close the bracket, log of 5, close it, and there we go. Whoa. So that is equal to 0.03. There we go. So that's the type of problem we can have, is just to change it. But a more common type of problem we could have are ones involving words. So the number of bacteria in a culture triples every day if the culture started with a population of 25 million. How many days later will the bacteria population reach 150 million? Answer in exact form, correct to the nearest tenth of a year. So what we're going to do is we're going to start off by saying let P be the population of bacteria and N be years. Okay, so we want the nearest tenth of a year. Okay, so then we get this formula that says P, the population, is equal to, now it starts off at 25 million, so I'm just going to put 25. We know our answers are in millions, but we just do 25. Okay, so 25 million is the same as if I just, bring it down. So I'm going to do 25 times, and the number triples. So it's going to be 3 to the power of n, and n is going to be every day. So this should probably be days and not years, I think. I don't know why I wrote days, years. Okay. So what we're going to do first off is we're going to start off by putting in, well, we want to know when the population reaches 150 million. So we want to know when P is equal to 150 million, or just 150 in this case, okay? Because a million will just come on the end anyway. Okay, so what we're going to do is sub P equals 150 into this. So we get 150 is equal to 25 times 3 to the power of n, okay? Then next thing I'm going to do is divide both sides by 25 to get the 3n by itself. So we get 150 divided by 25, which is not a stroke like that. It is in fact 6, and that is equal to 3 to the power of n. Okay, is that? Yeah, it is. Okay, so 6 is equal to 3 to the power of n. Okay, so now to get n by itself, we're going to do our we're going to change this into a logarithm. So we're going to get, so it's going to be log base 3 of 6 is equal to n. Okay, and then we're going to do our change of base. So it's going to be log of 6, log base 10 of 6 over log base 10 of 3. And this is going to give us how many days it should take for this thing to change. So let's substitute, or let's not substitute, let's put our values in, log of 6, because our calculator does log base 10 for us, log base 10 of 3. Put it in and we get 1.6. 3 ... So it would take approximately 1.63 days to get to 150 million if it tripled every single day. Okay. I feel like that was done wrong. I feel like that's wrong. I feel like that's really, really wrong. No, that'd be about right. 25 million would triple, so in one day it would go up to 75 million. 75 million, if that tripled, that'd be huge. So yeah, I think that is right. So cool. Awesome. 1.63 days. Very good. All right, with that being said, we're going to leave that one here, and we'll have a look in our next video at some exponential, or sorry, some quadratic exponentials.